So, in the last class we saw the spectrum can be identified in other ways. One was the set of points where this resolution of identity jumps, other was as the support of the spectral measures involved, right. So, either way one can define the or you get some set which is equal to the spectrum of the given operator. So, we will continue now we will start with commuting family of self adjoint operators. So far we were dealing with a single operator which was self adjoint or normal. We proved a spectral theorem for such operators. Now we look at slightly more general situation where you have a finite family of operators, let us say A1, A2, A3 and An, where Aj's A1, A2, A3, An are self adjoint or normal, but they commute. So, this is something you might have seen in the finite dimensional case. If I give you let us say 2 self adjoint operators or 2 normal operators A and B on a finite dimensional space. So, that is just a matrix, right. So, A and B are 2 matrices, normal matrices, and if they commute then you can simultaneously diagonalize them. That means, there is a spectral theorem for the for A and B together, right. That means, there is an orthonormal basis with respect to which both A and B are diagonal operators, right. So, one way to do that would be you first diagonalize A and then see that B preserves the eigenspaces of A and B restricted to the eigenspaces of A is also self adjoint. So, you can diagonalize B there, right, and that will do, right. If you remember, that is how we did the spectral theorem for normal compact operators. We did this for self adjoint operator, and then for normal compact operator we looked at the real and imaginary part, and then they commuted because the operator was normal, and we diagonalized one of them because both of them were compact, and the other one preserved the eigenspaces for the eigenspaces of the first operator, and we continued, right. And so, something like that we will do. Of course, it is slightly more complicated, but we can develop a functional calculus for commuting family of self adjoint operators and normal operators, which will lead us to a statement of the spectral theorem. So, that is what we will do, but let me give you an exercise first before we go to commuting families. Okay. So, let us start. So, exercise. So, this is related to whatever we did in the last class. So, let A be self adjoint, bounded, of course. Then, so spectral theorem tells you various things and you can deduce everything from that. One, A is positive. So, self adjoint is assumed. Okay. So, A is positive if and only if the spectrum is contained in 0 infinity, right, because once you have the spectral theorem, because A is self adjoint, you have the spectral theorem. So, it is multiplication by x somewhere on some measure spaces, the measures are supported somewhere, and A is positive, meaning whatever you are multiplying with should be positive. That means, x the function x going to x should be a positive function on the support of those measures, which is the spectrum, right, and the spectrum should be in the positive real axis. Okay. 2, if A is greater than or equal to 0, that means, if A is a positive operator, then there exists B which is also a bounded operator positive, such that B square is equal to A, right. So, you have a square root, that is what it means, right. You have a positive square root. If I have a positive number, I have a positive square root, right. This is precisely that. If A is a positive operator, there is a positive square root. Well, it follows immediately from realizing A as a multiplication by x on some measure space, because A is positive, spectrum is contained in 0 infinity. So, multiplication by x there is a positive operator, and you can look at multiplication by root x, right. Root x makes sense because x has to be positive. So, root x and it is a bounded continuous function on the spectrum of A. So, the operator corresponding to root x is your b, right, because when you square it you get multiplication by x and that is a, right. So, any positive operator has a square root. In fact, it is unique, but we will not bother about it now. Okay. 3, spectral mapping theorem. So, this is something again you have seen in some form or the other, spectral mapping theorem. Okay. Let f be continuous. So, f is continuous on the spectrum of A, that will do, but let us not think of it as a continuous function on the real line. Sigma of f of A, that makes sense because f is continuous. So, on the spectrum it is a bounded function and continuous functional calculus is enough. So, I have f of A, f of A is a bounded operator. I can look at its spectrum, right, sigma of f of A. So, sigma of f of A is something which you have seen in the case of finite dimensional and so on, right. If I know the eigenvalues of a normal operator eigenvalues of A, then eigenvalues of A square would be square of the eigenvalues of A, right. So, just f of lambda, where lambda belonging to spectrum of A, right. In other words, this is f of sigma I, right, the range of sigma of A under the mapping f. Well, again this follows immediately from whatever spectral theorem we know, because A is realized as multiplication by x. So, f of A will be realized as multiplication by f of x and its range, right, its essential range will be the spectrum of f of A, but f is continuous. So, its range and essential range are all same. So, it just f of lambda where lambda is in sigma I. Okay. So, all these are easy exercises, but it is it's good to write down the proof in detail, so that this is clear to you. Okay. So, let us continue to commuting family of self-adjoint operators. Commuting family of self-adjoint operators, okay, or normal operators, that we will do after dealing with self-adjoint operators. Okay. So, before we get on to this, let us define some things. So, let script A be a family of operators in BH. So, it is a family, it is not an algebra. Okay. So, some collection of operators, A be a family of operators in B of H, bounded operators on the Hilbert space H. Okay. Need not necessarily be an algebra, it does not have to be finite, it can be infinite or finite. Okay. So, A could be just A1 A2 AN, script A could be A1 A2 AN, n bounded operators or infinitely many bounded operators. Okay. So, all those possibilities, because for the definition we do not have to bother about this. Okay. Let take a vector in H, the cyclic subspace. So, we have seen this, but I am defining this in the general setting. The cyclic subspace for X generated by A, generated by script A, this family of operators is the, so the definition is the smallest. See, right now A is not self adjoint and so on, right. The script A is a collection of operators, there is no self adjointness there. We will come to self adjointness soon. So, this is the smallest closed subspace that contain X, right. So, it should have X and it should have all the powers of operators from A acting on X, right, but not just powers of operators from A, its adjoints also. Okay. So, it contains X and should be invariant under both A and A star. Okay. So, should be and is invariant under everything from script A and its adjoint, right. So, invariant under A comma A star, right, where A belongs to script A. So, all these operators, right. So, you look at all the operators in script A, look at their adjoints. So, you get a collection of operators and you look at the closed smallest closed subspace containing the vector x and invariant under A and A star. In the case of self adjointness, A will be equal to A star. So, there is no need to write that, it is enough to look at invariance under A, right. That is what we did when this in the case of the single operator. You look at x, Ax, A square x, A cube x and so on, sorry V, right, that contain, oh I wrote x, okay. So, you look at the span of those things and that would be automatically invariant under A, right, and A is self adjoint. So, it is invariant under A star also, right. So, this is the general definition of the cyclic subspace generated by a family of operators, okay. So, that is an easy definition. So, note that if script A is equal to A1, A2 etcetera an. So, these are bounded operators. So, script A is a finite family of self adjoint operators. To note that A is equal to this self adjoint and commuting right. So, what does that mean? That means for each Aj is self adjoint, that is Aj star is equal to Aj and they commute. So, A1, A2, An they all commute. So, Aj Ak equal to Ak Aj, right, for every j and k, right. So, it is a finite family of commuting self adjoint operators. Then what is the cyclic subspace generated by S? So, then the cyclic subspace for x is, well, is simply you apply A1, A2, An as many times as you want. See, they commute. So, it does not matter which order you apply, right. So, I will write it down as A1 to the L1, A2 to the L2 etcetera An to the Ln, right, acting on x, right, because this makes sense. It does not matter if you look at A2 acting on x and then apply A1, that is A1 A2 x, that is same as A2 A1 x, right, because of the commuting. So, it does not matter which order you apply these edges, you can pool them together, right, all the A1s you can put together, all the A2s you can put together and so on, and then you apply on x and then you take the span closure of this, right. So, all the Lj's will be positive integers 0, 1, 2 and so on, right. So, you look at this, you look at the span of this and take the closure, right. That is how the cyclic subspace for x generated by this finitely many operators would look like. In the single case, there was only one operator and we simply look at the powers of that operator acting on x, take the span and the closure. Okay. So, what is our aim? Aim is to prove spectral theorem for commuting family of finitely many self adjoint operators. Okay. So, for finite family, that means finitely many, okay, finite family of commuting self adjoint operators, okay, of course bounded, okay, we only look at bounded operators. Alright. So, as in the case of single operator, we have these versions, right. So, we will not get into all kind of versions, we have the spectral measure version and the continuous functional calculus, right. Continuous functional calculus will as usual give you L infinity functional calculus and so on. So, I will be brief because most of this will go through as in the case of the single operator, but we will prove one of them. So, that we know that everything else follows as in the case of the single operator. Okay. So, let me write down the at least two versions of the spectral theorem for a commuting family. So, let us start with the first one. So, theorem, first we will do the spectral measure version, where we identify the operators as multiplication operators, right. So, in the case of single operator, if A was a self adjoint operator, we realize it as multiplication by x with respect to some measure. First what we did was we looked at the cyclic case, right. That means there was a cyclic vector and then we got a measure, and then we started with one vector, generated the cyclic subspace, applied the result, we got one measure, then we look at the orthogonal complement and then go ahead and take the direct sum, right. So, it is enough to do the cyclic part, right, and then we can take the direct sum, except that we lose the uniqueness, because everything will depend on what vector you are starting with and so on. Okay. So, let me write it down. Let script A be a finite family. Okay. So, A2, A1, A2 etc. An. Okay. So, these are self adjoint, commuting is important, commuting family. Okay. So, Aj, that means Aj star is equal to Aj for every j, and Aj Ak equal to Ak Aj, right, for every jk, right. That is what you mean by a commuting family of self adjoint operators. Okay. Now, so we will write down the cyclic case first and then say that everything can be done as in the case of a single operator, right. So, let V in H, so all these operators are acting on a single Hilbert space H, right. So, let V in H be a cyclic vector, for A, right, the family A1, A2, An. What does that mean? So, we know that if the self adjoint and commuting is there, we know how to write down the cyclic subspace generated by a vector, right. So, that is, you look at all A1 powers of A1, powers of A2 etc. powers of An acting on the single vector V, right, and you look at the, so yeah, maybe I should write L1, L2, Lj's are 0, 1, 2, right, all powers, right. So, you do that and you look at the span and you look at the closure of this should be the whole Hilbert space, right. So, that is what you mean by a cyclic vector V, right. So, the V is here, right. You apply monomials in A1, A2, An, right, that is what it means essentially, or polynomials in A1, A2, An. Polynomials in A1, A2, An makes sense because A1, A2, An are commuting, right, otherwise it is a problem, right. X y and y x are same when you write variables, but A1, A2 and A2, A1 need not be same if they are not commuting, right. So, commuting is important here. So, you get the cyclic subspace and assume that is H, which is same as saying the vector V is actually a cyclic vector. In that case, we have a unique measure which gives me, which realizes these operators as multiplication operators on some L2 spaces. Okay. Then, so we will see where the measure is realized in the single operator case. If the operator was A, the measure was supported in minus norm A to norm A, right. Here I have n of them. So, all of them are going to be realized on the measure is going to be realized on the product of these sets minus norm Aj to norm Aj, which is an interval in the real line. You look at the n-fold product of that, that means it is a subset in Rn, and each Aj will be realized as multiplication by xj's, the jth coordinate. Okay. So, then there exists a measure. So, the measure is still 1, okay, there is only one measure which does this. There is a measure mu, well, which will actually depend on the cyclic vector, right. So, it depends on the cyclic vector V, also the commuting family, right. So, script A, but I will not make the notation complicated by putting V and A and all that, it will be clear what we are doing. So, there exists a measure mu on, so I should tell you where, right. So, this is minus norm A j comma norm A j. So, that is an interval in the real line, right, closed interval. You look at the product of this intervals j equal to 1 to n, right. So, this is sitting inside R n. Okay. So, I have a measure on R n whose support is in the product of these intervals, right, and a unitary map, and the unitary map U. Well, the U will go from the Hilbert space H to L2 on this space, the product of these intervals with respect to the measure mu we have, right. So, that would be L2 of the product space or Rn, right, does not matter because the support is in that product space, right. So, j equal to 1 to n minus norm Aj comma d mu, right. So, we have this huge Hilbert space H identified with L2 of this product of intervals. So, that is my set which is sitting inside Rn, and with respect to the measure mu which we can construct such that the operator A1 A2 An can be realized on the other side as multiplication by xj, right. So, such that, well, so first of all u of v. So, v, what is v? V is a cyclic vector in H. So, it should go to the cyclic vector on the other side, right, and that is the constant function 1. So, this is equal to 1, that is the constant function 1, right, because we are going to realize, see, this is sort of force, right. Once you realize the Aj's as multiplication by xj, we will have to go to 1, because any monomial in Aj's applied on V will go to corresponding monomial on the other side, right. So, polynomials in Aj applying on V will go to polynomials on the other side, and polynomials are dense, right. So, you will get all L2, right. On the left hand side you have polynomials in A acting on V which is a cyclic vector. So, you will get a dense subspace of H, right. So, that is how the unitary comes. So, that this goes to 1, and the U Aj U inverse. So, U inverse will go from L2 to H, Aj takes H to H, U takes H to L2 back, right. So, this has to act on a function psi, right, which is on the L2. So, I should tell you what it is at the point x. X is where is the point x? X is in Rn, right, it is in the product space. So, this is simply xj, that is jth coordinate psi x. Okay. So, x is equal to x1, x2, etc. xn, right, and this would be in this product space, right, j equal to 1 to n minus norm Aj. Okay. So, that is how the statement in the commuting case looks like. Okay. Let me also write down the continuous functional calculus, and then we will prove the continuous functional calculus just like what we did in the case of single operator. I mean the proof which we did for resolution of identity and so on, right. We created the continuous functional calculus. The advantage is that we have the continuous functional calculus or the resolution of identity etc. for each of the operator already. Okay. So, the work is slightly simplified. So, spectral theorem, this is the continuous functional calculus form. Okay. So, continuous functional calculus form. Okay. So, again So, we start with the family which is self-adjoint and commuting. So, let script A be equal to A1, A2 etcetera A n self-adjoint and commuting. The continuous functional calculus will tell me that there is a star homomorphism from continuous functions on this product set, right. So, there exists a star homomorphism. So, continuous star homomorphism. So, there is a continuous star homomorphism. Well, from so we can call it, give it some name. So, let us we denoted it by capital phi, right, in the case of single operator phi sub a or something like that. So, this is, let us call it phi sub a1 a2 etcetera a n, just to say that there are n many. We will simplify the notation later. So, the star homomorphism will be from, so phi a1 a2 etcetera a n has to go from continuous functions on the product space, right. So, continuous functions on j equal to 1 to n norm a j minus norm a j to norm a j, right. In the single operator it was just one interval, that is the only difference, right. So, you have continuous functions on this compact set, two bounded operators on the Hilbert space H such that so if you recall all that for the single operator, you will see exactly that is what is happening. The constant function 1 should go to identity operator, right, it is a star homomorphism, but the a1 a2 a n should be identified with the coordinate vectors x1 x2 xn, right. So, if I look at the function x now is in the product space. So, it has n coordinates, right, x is x1 x2 xn. So, x1 x2 xn going to xj, that is a continuous function. So, that will go to the operator aj, right. In the single operator case, it was the identity function which went to the operator a, right. Here the projection to the jth coordinate will go to the identity jth operator, right. When I say projection to the jth coordinate, this is x1 x2 xn going to xj, right, that will go to the corresponding operator aj. So, let me write down that such that phi of a1 a2 etcetera a n of the identity, well, identity maybe I should simply write 1. So, this is the constant function 1, right, will go to identity operator. So, where 1 is the constant function 1, right, constant function 1, right, because that is the identity for the algebra of continuous functions on the space, right. And what is more important is the functions, and if I look at the id j as a function. So, id j at x equal to x j, right. So, x is equal to x1 x2 etcetera xn, right. So, if I look at this function, this is a continuous function, right, this is a continuous function on that product space. The image of that is the jth operator. Then phi a1 a2 etcetera a n of this function idj, id sub j, right, that is the function x going to xj, right, that will be aj, which is a bounded operator on our Hilbert space. And of course, the homomorphism is continuous, right, and we have a precise estimate. If I look at phi a1 a2 etcetera a n of any continuous function, the operator norm is going to be less than or equal to the supremum norm of f. So, f is going to be defined in the product of these intervals, right, it is a continuous function there, and the operator norm of the image under this homomorphism phi is less than or equal to L infinity norm of f, right, the infinity norm. So, if there is an appropriate spectrum, so spectrum we may not define what is known as the joint spectrum of these operators. If there is one, then there would be an equality, right, at the continuous functional level we know that there is an equality, but we may not get into that. Okay. So, we will prove the continuous functional. Okay. So, maybe let us stop here, we will take up the proof in the next lecture. Once we have the continuous functional calculus, we have the L infinity functional calculus also, right. So, we will be able to define the functions of these operators, right. So, if you look at phi a1 a2 an of f, we will denote it by f of a1 a2 an, right. So, that is how we denoted in the single operator case. So, any f when to an operator f of a, right, or t sub f depending on the notation we have. Similarly, we will be able to define f of a1 a2 a3 an for any bounded function on this product space, right. That is the L infinity functional calculus, and that was just one step from the continuous functional calculus, right, and define those measures and then extend it. So, I will give only a sketch of what needs to be done at that point. Okay. So, we will stop here, we will take up the proof in the next class. Okay.